So my name is John Caz, and I'm going to talk to you today about parallel I/O. Okay, so a little bit about I/O and HPC applications, and this has been pretty standard up until recently. Almost every application started with a big read, then with some frequency there were writes, then a big write at the end for a restart file, and then you were done. Although now, with machine learning, it seems to be a lot of reading and writing, and the file systems are stressed in different ways that we're still learning. So I'm mostly just going to talk about I/O, parallel I/O that we see in HPC, traditional HPC. One of the things about I/O is most of the developers don't think about it until it breaks. And then they think about it, or until they get stopped from running because they broke the file system and, they ruined the party for everybody. And so what I want to do today is explain to you how a parallel file system works, because it's this really sophisticated piece of software that when it works, you just don't even notice it. It's just like magic. And if you think about what it's doing, it's letting you write from tens to hundreds to thousands of nodes to a single data space that is also spread across multiple disks or flash. Okay, so how do you do parallel I/O? So you're doing it every time you run and you use the parallel file system. You may not know it, but underneath the covers, the file system is writing to a series of disks, multiple RAIDs that are spread out. And so even when you write your simple output, your little text output file, you're actually doing parallel I/O. Now, when you get larger and more sophisticated, then you'll use tools like MPI/IO and Parallel HDF5 to work with the parallel file system to do it efficiently and at large scale. And so what I'm going to try to explain to you is how these parallel file systems work, so you have an understanding on how to scale out your code to be a good citizen and use it effectively. And so I'm going to talk a lot about Lustre, because most of the large file systems out there are Lustre. And I'll mention BGFS. It's another popular file system, and it's very similar to Lustre. So, Lustre. What you have from Lustre is clients are where you are, right? You're running on a node in an HPC cluster. There is a Lustre client per node. This controls your access to the file system. You don't notice it because you just do regular POSIX I/O operations: open, close, seek, read, write. But underneath the covers, it is coordinating your access to the actual disks on the back end. And so Lustre has what's called a metadata server, and you can think of that as sort of the traffic cop. Basically, the bouncer that watches the door. And that's what lets your data through, and it tells it where it needs to go. So when you open your file or close your file or do a seek, it goes to the metadata server, and it tells it where this data is going to be written, how it's going to be distributed, and how it's going to be split up, or if it's going to be split up. And it gives the client all the information it needs. Now, after that operation happens, when you do the reads and the writes, the metadata server is no longer involved. So the problem here is that all the nodes that are controlled by the metadata server, that's the bottleneck, right? Everybody that reads or writes to those nodes, when they open or close that file, they have to go through the metadata server. And so this is why it's really bad to open and close files a lot. You should open them once at the beginning of your code and not close it until the very end, because all these operations have overhead. And so where the data goes in Lustre is something called an OST. It goes through an OSS, which is basically the computer that controls the data flow. And on the back end, there's an OST. This is just a RAID. And what Lustre does is it carves your file up into what they call stripes. And it spreads it across these OSTs. And this is where you get the parallel bandwidth from the parallel file system. The fact that you can write to multiple servers at the same time. And so if you're on a Lustre file system, you can run this command, lfs osts, and see how many backend servers do you have. And so we've been doing our labs on bridges, and if you run it on bridges, you'll see that home has 12, and your sort of scratch area has 24. And I listed the other system I'm most familiar with, ours at TACC, Frontera. And on this system, notice over there on scratch, we actually have 3 separate file systems. And the idea here is for different types of operations. One is for like the regular user, one is for the problem user who causes other people problems, and one is for the power user. And the one for the power user is the one with the most OSTs, because that gives us twice as much bandwidth and twice as much size. And so each of these file systems have their own set of metadata servers that control a subset of the files. And so this is what's happening under the covers when you read and write your files on a Lustre file system. And so one of the key concepts for Lustre is striping. And so when you write a file, Lustre, or when you create a file or directory, Lustre has a default stripe count and a default stripe size. So by most file systems I've worked on, the defaults are 1 megabyte and 1 stripe. And the reason it's 1 megabyte and 1 stripe is that works well for general I/O. Right? If I'm writing a bunch of small text files, I probably don't need multiple stripes or really large stripe size. Now, what's nice about Lustre is you can change this. You can change these settings. So you can optimize the stripe count and the stripe size for your particular workflow. And so here's just a simple example of an 8 megabyte file with 4 stripes. And it literally just takes the first megabyte and writes it to one server, the next to another, and the next to another. And you can do this right also in parallel. And so what Lustre supports is, this is an example of one process, writing, right? Here's an example of many processes trying to write to the same file. And so each process writes its data, and it gets written to one of these stripes. Now, this can be chaos, right? If all of these processes are trying to write to the same stripes at the same time. What you can do with Lustre, though, is organize the chaos, and this is something MPI-IO can do for you, so that the writers are not stepping on each other's toes. And so you have only one writer per stripe. And so the other problem here is each one of these tasks, they all open these files. So if I have 100,000 tasks all opening the same file, they're all going through this one metadata server. So it's going to take it a while to satisfy all these requests. And so this is another reason to use parallel I/O, because what will happen if you use MPI-IO correctly, it won't be 1,000 or 100,000 requests. It'll be a handful from the actual tasks who are actually writing to the file. And so when you need high bandwidth I/O, you basically want more stripes. Now you might think, well, if my file system has 16 stripes, I want to set the stripe count to 16, but no. In general, you want to set it to about half or 2/3 of the total number of stripes, because when you start, there's almost certainly going to be 2 or 3 back-end servers that are just overloaded and busy. And when Lustre creates the file and it chooses which OSTs to use, it will basically choose the ones that are least busy at that point in time. Now, the little bit of problem with this is that when you create a file, it's frozen. The stripe size and the stripe count are part of the file metadata, and you can't change that. You can create a new file, or you can create a new directory with default types and write to that. But you can't change the type of the file. And so here's just an example of some of the commands you can use on a Lustre file system to get information about your file, and how you can set the stripe size, you can set the stripe count, so you can determine what the file system is going to do and how you're going to use it. Now, this is, as far as I can tell, fairly unique to Lustre and BGFS. Most of the other file systems, they don't give the user any control at all. The admins get to determine how everything is configured on the back end. So what this also means is that when you bring the file system down, you're partly responsible because you have not set these parameters correctly. And so here's just an example of a code we worked on, my God, I guess it's been about 12 years now. Flash is a supernova code. A lot of people probably heard about it. And on one of our older systems, we had around 300 OSTs, so we had a lot of bandwidth on the back end, but spread across a lot of OSTs. And a couple of colleagues of mine worked on this to parallelize the output. And you can see how quickly they brought the I/O times down by a factor of almost 10 for the reading, and a factor of about 2.5, 4 times for the writes. And really, all that took to do this was setting some environment variables and presetting some directories, running some Lustre commands. So BGFS is a file system very similar to Lustre. They don't have stripes, they use chunks, and they have a chunk size, but other than that, it's pretty much the same philosophy. You can set the chunk size, you can set the number of chunks, but only for a directory. For some reason, it won't let you create a file this way. You create a directory, and any file you create in it is set to these defaults, but then you can change the setting on the directory. And so these commands I'm talking about, the Lustre commands, you have the same commands in BGFS. They're analogs to it. And so we have a BGFS system, and I have some parallel I/O benchmarks, and basically I just took all my Lustre commands and translated them to BGFS to operate there. And you get the same type of information from the file type. So, Lustre can be very powerful, and if you use it at large scale, it's very performant, but it's also very, very fragile. So, we have users who just running from one node of Python code can bring the file system down. And what's happening is their workflows are accessing many, many small files over and over and over. And this causes a load on the metadata server. And so when the metadata server can't respond, then everybody else's I/O operations slow to a crawl. The other way Python can hurt us is the Conda environment. How many people here use Conda? Okay. So, if you're using Conda on your HPC system, do you have the environment activated all the time, or do you just activate it when you need it? Anybody? All the time? Great. Because when you activate it all the time, what happens is you run a large parallel job. Every task runs through the bash shell. It starts up that way. That loads the Conda environment. And so then you might have 100,000 tasks trying to load the Conda environment. And that causes quite an overload. And so, yes, if you use Conda, please only enable it when you need it. Because we have a lot of users, they just install it and they activate it, and they leave it activated. And so what we've done is we've actually hacked our default bash script. So if you run on our systems, if you're not on the first node, it exits before it gets to the Conda activation. And so you'll only get the Conda environment on the first node. And that's limited the amount of, let's say, file system slowdowns we've had from Conda. And so basically, when you think about how the file system works, think about how you're interacting with it. And that's where this too often, too many, right? So too many open closes or seeks, you don't need to do that, don't. Too many small writes or reads, if you can buffer up your writes so you have a fairly large amount of data to write, then do that. So maybe run for 1,000 time steps, collect all the data, and then write it at once. So too often, too many. Try not to do that. And also, use the appropriate file system. Most systems have a scratch file system and a home file system. You should not be writing large files to home. You should not be doing intensive I/O to home. I mean, I know it's backed up, and you don't have to worry about your data being removed there, but in general, the home file system is not designed to support that type of load. Also, LS. Someone in their wisdom in Red Hat has decided, or maybe this is just bash, that LS should by default be alias to -- color equals TTY. What this does is LS is kindly showing you information about every file in the list, which means it stats every file in the list, which means in a directory, it has to walk through each inode to check on this file to the metadata server. This is a serial operation. So if you have 50,000 files in your directory, this is going to take a while. So first thing I always do is basically unalias LS or alias it to exactly what I want. And if you want to get around this, you can just do \ls and then it won't use the alias. And so if you find yourself in a directory and you're like, why is it taking so long to list these files? \ls, you'll get the list. You won't get any data about them. You won't know if they're executables, you won't know if they're directories or anything, but you will get the list. This is also a reason when you write files and you have a lot of files, build a hierarchy of directories. So within each directory, you don't have more than a few thousand files. Then you can traverse these directories and these file lists pretty quickly. Because if you have this one directory with this huge number of files, as your program tries to open these files or search for them, it's going to be slow. Oh, and it will probably break your wildcard. You might do ls something star, and it just goes buffer overflow or something. Question? Yes? Okay, so say what kind of file system is what? So our home file system is Lustre. On many systems, the home file system is NFS, and it has its own issues. And usually the issue with NFS is sort of lazy updates and a lot of .NFS files while it's trying to sort of clean things up under the covers. And the reason I say don't use home is when you build a Lustre file system, you dedicate a certain amount of resources to it. And so for home, you don't dedicate a lot because it's usually smaller. And people always ask us, well, why do I have a quota on home? Why can't you make my quota not 10 gigabytes, but like a terabyte? And it's because we back up home, right? So your home file system is always backed up. And so it's not maybe that I can't make it a terabyte, it's that if it's a terabyte, I can't back it up. And so that data is not going to be saved. And so home is restricted in this way. Oh, what was the other question? We do. Lustre is on our home file system. Because I don't want to spend as much money on the home file system as on the scratch file system. Right? So the scratch file system is larger and has more bandwidth. And when I build the system, I have to decide where I'm going to allocate my money. And so if I build like I said, if I build a really large home file system, I can't back it up. It's too large. And so what we do is we have Scratch because this is performant. This is where we want you to write. But Scratch is never, ever, ever big enough. No matter how big your Scratch file system is, it will get filled up. And it's called Scratch because we can't leave your data there forever. And so it's sort of a matter of economics. Okay, so now I'm going to talk a little bit about the software that runs on these things. So if you understand how the parallel file system works and you have some controls and some hooks into it, you can use software packages that are designed to interface with it, and primarily parallel HDF5, parallel NetCDF, and that sits on top of MPI IO. And so MPI has built this parallel I/O layer that in some forms acts just like POSIX, just like open, close, seek, read, write at that level. But what's powerful is it has collective operations that allows you to collect all the data and do it in such a way that it appears as if you wrote it using a sequential program. And so these are the different patterns. This is probably the most common. People write their parallel code and they basically write everything out from task 0. So they just collect all the data to task 0 and write it out. They read all the data from task 0 and propagate it, because then they don't have to worry about how to partition the data from the file to the tasks. So task 0 handles everything. And for small task counts, this works perfectly fine. The other way they do it, usually when they start, is every task writes its own file. Now, this is usually the fastest and most performant if you don't overwhelm the file system. The problem is, what if you want to change the task count of your program? What if you want to change the size of your grid? Every time you make changes, it's hard to adapt to the changed code, right? Because you've stored your data in a very structured, restricted way. And so you might need to go from 5,000 files to 10,000 files to scale up. So then you have to write a program that repartitions the data. And so this doesn't scale well. And so ideally, what you want to do is have all the tasks write your data to a single file. And by this, I don't mean all your data, I just mean one large data structure that is decomposed across many MPI tasks. You want to write it all to one file, and ideally in a way where it doesn't matter how many tasks you're using to read or write it. And so this is where MPI I/O comes in. This is what it was designed for. Screen. And so reading and writing in parallel is similar to communicating an MPI between tasks. So we have read-write commands that are like a single task. So this is like a send and a receive, right? Send is a write, receive is a read. And then we have collective parallel I/O tasks, and these are like the collectives we have, like all gather, broadcast, things like that. And you're communicating with the file system, right? You're not communicating with other tasks, you're communicating with the file system. So it's just another data store. And so if you're comfortable with how you work in MPI, sending and receiving data, both point-to-point and with collectives, you should catch on to how this is working with parallel I/O. And so what happens is when you use the MPI file commands, and they're analogs to the POSIX commands, open, close, seek, read, write, and they have a lot of the same options. There are some that are a little different, like this MPI file seek shared, where you can share a pointer. But to be honest, I've never once used that. I've never had the need. And then when you see read at and write at, that's basically where you're saying, I'm going to tell you where to write this, but I'm not going to use the file pointer. I'm going to use a byte offset to say where in the file it's going to be. Now, when you use these commands to open a file, you can open read-only, write-only, read-write, create. And so just like with POSIX, and the advantage here is if you're only going to read, please open it read-only, because what that does is it puts a read file lock on the file. So that means other processes can also open the file for read-only. If you open it read-write, what it's going to do is while it's open, it's going to try to block everybody else from writing. And so this is just an example of seek. And read at here, which I just talked about, just lets you set an offset to where you want to read from the file. Okay, I'm going to go. So the only command, I'm going to talk about set view in a minute, and set view is important for the parallel writes we're going to do. Otherwise, the write and the write at, they act just like a write. So these are like This is like an MPI send. So this is like from a task, one task you're writing to the file. And so this is where you can get in trouble, because if you use this on 10,000 tasks, you've got 10,000 tasks all trying to write to the same file. And even if you've got your offset set right that you're not writing at the same point in the file, remember I told you the way Lustre works is there are these stripes. And so within that 1 megabyte stripe, you might have multiple tasks trying to write into the same stripe. And so they can't do that at the same time. And so this is where the view is important, because with the view, you can set what area of the file the task is going to see. And so this is like exposing just part of the file to the task that's opened it. And so here's an example where you've set a view and you've mapped it to the file. And so you have a data type that you're going to write, and then with the view, you've set it with like an offset and a stride. And so when you write it, it goes to this piece of the file. So this is important because using tools like this, you can control how you write to the file so it appears as if it was written by a sequential process. And collective I/O. So to me, this is the power of MPI I/O. This is how you want to use it, what you want to do. And this is where you're having every task call these collective operations, but under the covers, interfacing with the actual file system are a small subset of tasks. And if your MPI is Lustre aware, it will work with Lustre to not overwhelm the system. If your MPI is just parallel file system aware, what you can do is you can control the number of writers. So you can set it so it's not going to overwhelm the system. And the beauty of using these techniques is you don't have to worry about the data movement, right? So let's say you're running 256 tasks, but you only want 16 tasks to write. So you can tell it, I want 16 tasks to write. But when you call this, underneath the covers, MPI moves the data to those 16 tasks, and they do the writes. And you don't have to worry about the data movement. And so collective I/O calls will always have the word all in them. And so I don't have it in this one, but in these slides, but in the, I think MPI 4, you also now get asynchronous I/O calls. So you can have MPI file read all begin, MPI file read all end. So you can basically start the operation, go off, do something else, and come back, just like asynchronous communications. So another valuable thing is MPI-O hints. So you can put hints in an info object. And this comes in handy because you can set these things I talked about with Lustre, striping size and number of stripes. Now, this only works when you create a file. You can also set the number of writers. If you don't set the number of writers and you use Lustre, MPI-I/O will default to the number of stripes. And so this is why some people, they use the collective operations, they run on a Lustre file system, the default stripe count is 1. So what this has done is it has basically limited their write to a serial write. And so under the covers, what's happening is all the data is going to one task, and it's being written by that one task. And they're like, well, you know, I'm doing parallel I/O, why is it so slow? And it's like, well, Lustre's enabled, and you haven't changed the stripe count. So it doesn't know how to write in parallel. And so here's just some examples of how you set it. You basically set up an info object, and you add data to the info object. And when you open the file, you pass it this object. And so here's an example where I set the stripe count, I set the stripe size, and then I've overridden the number of writers, and I've actually set the number of writers with this parameter called CB nodes, collective buffering. And that tells it, well, I want you to write with this many writers explicitly. And so a good rule of thumb, if you can, if you have enough OSTs on the back end, set the stripe count to the number of nodes you have, unless it's all the OSTs. Otherwise, set the stripe count to about 3/4, 2/3 the total number of OSTs. Because what you're trying to do is get the maximum bandwidth you can without running into a slow node or overloading the system. Now, unless, if you're the only one running on the system, so one of the things we do on our system is we'll have a week where we'll let users use the whole system or half the system. So if that's what you're doing, then you might take all of them, right? Because there's not going to be much competition because nobody else is running. And so here, I'm just going to cover very quickly an example of writing a 2D distributed array. So you have your MPI program and you have a 2D array, and you're going to distribute it over 4 tasks. Now, this example is in Fortran, so if you don't know Fortran, you're going to see some. But if you know C, you should be able to follow this pretty easily. The main thing is that it's column major, not row major, right? So the data basically goes down first, then across. And as you can see in this, do I have a pointer? No, I guess I don't have a pointer. As you can see in this example, basically you write the first word, there are 4, so this is a 8x8 array decomposed across 4 tasks in a 2x2 decomposition, right? And so the idea is I want to write out this data, but I want to write it to the file as if I wrote it from a serial program. It's just the data I'm writing to a file. But in reality, it is decomposed. And so it's not simple to do this on your own, just from each task to figure out where in the file it goes. You figure out the offsets. That's hard. And really, it's a little harder than that because your data probably has shadow cells, right? And so the real array isn't 4x4 on each node, on each task, it's 6x6. But the data I care about is interior. It's just the inner part of this array. And so that's the 4x4 part I care about. I don't want to write the shadow cells because they're not part of my real output. And so now what I need to do is somehow map that interior data to that file. And for those of you that were in the MPI training earlier, the way we do this is by setting up data types. So we can use the subarray command to set up a data type that is basically a template for this array. And so we set this up by setting offsets and sizes using the subarray command. We create a type and we commit the type, and now we can use it. And now I can take this data type called local data, and if I apply it to any array of this shape, it basically is a template that says, oh, only access that shaded part. And so I do a little setup for this, and I can use it for all my data structures as long as they're of this type. And so what I'm doing here is I'm turning this local mapping into a sequential set of data. Now, when I say global mapping, what I'm talking about really is the actual file system, the file it's going to be written to, right? And I think of that as the global data space. So this is the local data space. This is what each task sees. On the global data space, the data is not contiguous, right? Because you come back up here, I have one column on task 0, then I have another column on task 1. And that's how the data is going to be laid out in the file, because that's how it's going to write this array. It's going to write 1 through 8 in column 1, then 1 through 8 in column 2. And so somehow I have to map that to the file. And so this is where I create another data type, and I'm going to call this one, what did I call it? Global data. And so now this is the mapping to the file. And so I've got sizes and offsets of the global file space, right? So this is an 8x8 array This is the global array I'm writing to the file. And so to use this, I use that set view command. So first I open the file. I have info null. In this example, I haven't set any stripes or writers or anything. I'm just doing something fairly simple. And then when I set the view with this global data type. So this tells me how to map the data to the actual file. Now when I do the write, I use my local data type. And so now that I've set this up, I can write this file out or any data structure to the file in this way where it appears in the file, the global array that you had decomposed is in the file written contiguously. And so now you can take this file and read it in with a sequential program, with an analysis program, or you can read it in with your code right here using the same data types. And if you do this, if your code's set up correctly, you can change the task count, the number of tasks you're using, and still read and write the file. And it will come out the same every time. Sort of this is the power of the collective operations. Questions? Y'all are quiet. Okay, so, and then there's HDF5. HDF5 sits on top of MPI-IO. And HDF5 is well, let me change that. HDF5 is a file format. So there's serial HDF5 and there's parallel HDF5. Parallel HDF5 sits on top of MPI-IO. Serial HDF5 is a serial I/O operator. Now, HDF5 is a file format, hierarchical data format. That's what HDF5 stands for. And what's nice about this is you can open an HDF5 file. You can write metadata that basically describes what's in the file. You can write many different data structures to the same file. And with the metadata, you can describe it in such a way that other programs can open the file, read the metadata, and figure out what's in there, and then unpack it for you. And it's such a widespread standard, almost every data analysis tool will have a way to open and read an HDF5 file. Now, when it gets powerful is when you use it in parallel. I think I just said most of this. Now, it's a little bit more, I find it more difficult to use in MPI-IO because of the way you map the local data to the file and sort of the global data file picture. And it uses, well, I've used hyperslabs. There's another technique too that I don't think I've ever really used. But it does provide an efficient way for you to store data and, like I said, support it pretty much everywhere. But the best thing about it is it runs on top of MPI-IO. You can get the parallel HDF5 and everything I've talked about, like the info, setting stripe count, stripe size, all of that applies. About the metadata. And so if you use parallel HDF5, you can write your one file or your multiple files from however many tasks you want. It uses MPI-IO underneath. It works with Lustre. It works with all the file systems. And it is constantly updated and supported. Now, there are some other parallel file formats. There's NetCDF4, which NetCDF4 uses HDF5 under the covers. There's another one called pNetCDF, which sort of sticks to an older NetCDF framework, and it's used mostly in climate, weather, ocean codes. I think they're about the only people that use pNetCDF. And basically, HDF5, NetCDF, these are the most common file formats we see on our systems. Okay. All right, good. I'm right at the end. Okay, so general strategies for I/O. So when you're reading or writing, if you can, just like in memory on a computer, try to access the data contiguously. So if you are doing sequential I/O, try not to seek around, jump around in the file. Don't open and close the file. This is the too often too many. Try to bundle and compact your I/O operations. Don't write multiple files unless you're really sure you're not going to change the task count. I mean, I do have users who write not quite one file per task, but they basically are sophisticated enough. They have set up their own I/O infrastructure where they have hierarchies of directories, and they might write out 100,000 files. But they know they're only running the same size execution, and they're doing like a long-running model, and they get very good I/O performance. If you do something like that, make sure your file has one stripe. Also, like I said, if you can, use parallel HDF5. Use the libraries that are available. HDF5 has, I think, a fairly steep learning curve, but it is very useful. I use MPI-IO just because I'm familiar with it. It's easier for me to write a code in it, understand it, but it's still, that's just to write like files, binary files. They're not as sophisticated as the HDF5 files. And at the very least, if you do parallel I/O, whether it's Lustre or not, think about the number of writers and try to play with this number of writers to see what's optimum. It's hard for me to tell you ahead of time because this isn't a science. This part is an art. Once you start scaling out the I/O, the file system responds in ways you didn't expect. Something else that I did not cover here, but if you have to do a lot of scratch I/O, in other words, if you have to write and read from files that you're going to throw away, use local disk if it's there. Please use local disk because it is so much faster. And so we have specifically developed tools, mostly for Python, where if it's overwhelming the file system, we copy all these little object files to local disk, and all the future reads come off local disk. Because for these workflows, it's just reads, right? And so it doesn't matter if it stays on the parallel file system. But remember, if the system has local disk, you might be able to use it. And we have some users, we make them do all their I/O on local disk, and then at the end of the job, they copy it to the parallel file system because the batch script, well, the epilogue script will clean off the temp disk, right? So if you leave your stuff there, it'll be gone. I think I've said everything. If you're on a Lustre system, think about the stripe count and stripe size, see what you can do. Pay attention to the I/O in your code. If you're just starting to parallelize your code, think about how you're going to write it as you scale out. And that's everything I've got. Any questions? Okay. Okay. Goodbye.